Hello and welcome to this video. We're going to start the topic of waves now, so we're going to look at a little bit of an introduction into waves and their properties. You will know a lot of this stuff from GCSE. Not much changes in the idea of properties because we don't really get any new properties so much. We're just going to take them and we're going to add in something extra. So this video here should just be sort of a little bit of a revision of GCSE waves and all of the properties that you would have met there. So you would have met at GCSE two types of waves. Those waves are transverse waves and longitudinal waves, but we'll get onto longitudinal waves in a bit. So you will remember that the definition of a transverse wave is where the oscillations are perpendicular or at right angles. Perpendicular is probably a better word to use. Are perpendicular to the direction of propagation. Okay, so this is just a bunch of fancy long words like oscillation, perpendicular, propagation. Oscillations should be a familiar word, so should perpendicular, but this idea of propagation, it essentially just means it's the direction that the wave moves in. It's just their fancy way of saying it to try and make it sound more scientific, but it means that that's the direction it goes in. But this is the wording you want to use in the exam question. So transverse waves look sinusoidal, so they look something like this, and I could keep doing this on and on, and they pass around something called an equilibrium line. Okay, so I'm just going to call this the EQ line, but EQ is just short for equilibrium, and this is essentially the 0 point. So this is how we're going to measure how much has something changed by, which we're going to call the amplitude. And everything basically oscillates around this equilibrium line. So the particles will go up and down around this equilibrium line. Okay, so what would the motion of a single particle in a transverse wave look like? Well, if we pick this one here, as the direction of the propagation goes in this direction, so this is the direction of propagation, as this next wave passes, this particle is going to come down to meet this point here, so it moves downwards. But then as soon as it reaches the bottom point here, it's obviously not going to move this way, but it would move directly down, and this whole wave would have moved across to meet this at that point. Then as soon as it reaches that point, it's then going to move back up. If we take a particle in the middle, so on the equilibrium line, next thing it's going to do is move down. But as soon as it gets to the bottom, it's going to move back up. If this point here meets this, it's going to move back up. So the particles inside a transverse wave move perpendicular to the direction of propagation, because the direction of propagation is horizontal and they are moving in the vertical plane. Okay, so now let's look at 4 properties of these waves that you have to be familiar with. So the first one is wavelength. So wavelength, we give the symbol lambda. It's a length, so it's a distance, so we measure it in meters. And all a wavelength is that it is the distance between two identical adjacent points on a wave. Okay, so what do I mean by two identical adjacent points? It just means that I could cut, so if I take this point here, I know the next thing this is going to do, if I were to trace this backwards, is move down. So I need to go along this line directly horizontal to find the next point that would also move down next. And the distance between these 2 points is the wavelength. So I could have this distance here and label it lambda, but I could also have this distance from here to here and also call that lambda. I could have from here to here and also call that one lambda. So there are multiple ways we can measure the wavelength, but because this wave is will have a constant wavelength, hopefully, as long as it's not passing through any other mediums, it should have a constant wavelength. All of these things should give you the same value. Okay, so that's your wavelength. We can also look at this idea of an amplitude. Now, an amplitude we usually just note as A. This will be the convention that we're going to look at again when we come to do periodic motion in SHM. And the units of amplitude are kind of a tricky thing to exactly lie out, because the amplitude of a wave can be different. If we're looking at a particular wave and we usually map them onto some sort of sinusoidal graph. So we'll usually have something that will be, so I'll draw a rough sketch here, something that will go time across here and then maybe displacement across here. And that displacement is the vertical displacement. So we're saying how high has it come? And in that case, this is going to have a unit of meters. But we could also map this onto another thing that where the y-axis isn't measuring displacement, but it's measuring the amount of power, because the power is proportional to the amplitude squared. Okay, so the amplitude can also be an amount of or related to the amount of energy that this wave can transfer, which kind of makes sense. If you have a much larger amplitude wave, it means that you've got much bigger displacement, so you've got a lot more energy to hold within the space underneath. But amplitude, I'm gonna, for the sake of this, note it as meters, because that's the kind of convention we're going with, but know that sometimes the unit of this amplitude might change a little bit, but we're going to go with meters for now. And the definition of the amplitude is that this is the maximum displacement from the equilibrium line. Okay, so I'm going to shorten it to EQ. Let me get rid of this. Equilibrium line. No. Obviously, in your exam, don't write EQ dot. You'd have to write the full equilibrium. I'm just shortening it here to save a little bit of time. Okay, so the amplitude is the maximum displacement from the equilibrium line, and it's this distance here. Okay, so this distance from the equilibrium line to the highest point, or even to the lowest point, we could label as A. That's the amplitude of the wave. Okay, and it is related to the power by squaring the amplitude, but that's not going to play too much of an important role just yet. We could also have a property called the frequency, which you will be familiar with. The frequency, we give the symbol F, and it is measured in hertz, and the frequency is the amount of waves that pass a point per second. Okay. Frequency is kind of like saying, well, it's exactly like saying, I have this point, I'm going to measure how many full wavelengths pass this point in a second. And so this is why we have this unit of hertz. It should technically be, because it's per second, if we wanted to look at the base SI units, meaning we go back down to the smallest possible dimensions that we have, this unit should technically be seconds to the -1, because it's per second. But this is going to get messy, so instead of saying per second, we just call it hertz. Now, the counterpart to frequency is something that we call period. Okay, so we can also look at the period of a wave. The period of a wave has the symbol T, capital T. Make sure that your in physics in general, don't mix up lowercase letters with uppercase letters because they usually mean two different things. In this case, an uppercase T will mean a time period, where a lowercase t will just mean like continuous time. It's a measure of time, so we measure it in seconds, and what it is it's the amount of time taken for one complete wavelength. I'm just going to put wavelength as lambda to pass a point. Okay, so these are your four main properties of waves that you need to be able to recognize and also do some calculations with. So let's look at how we're going to do a few calculations with these. So we'll keep the properties here. The one thing that we could work out first would be wave speed. Now wave speed, very similar to speed that you'd encountered at GCSE again. So we know speed is equal to distance over time. Now there's a reason we're not using velocity and displacement. It's because the wavelength is a distance, so it's a scalar value, so we can't have a velocity because both of these things are actually scalars, so we have to look at speed. But we don't want to confuse this speed with displacement in the mechanics topic, so all we're going to do is just give it a different symbol. Okay, so we call wave speed c. Okay, so it's literally just means c. The only reason that it literally just means speed. The only reason we change it is because we already have s for displacement, so we don't want to have two s's and make everything confusing. And we know this is going to be some sort of distance. Now we have two distances, but one is going to be in the direction that the wave is traveling, so it's going to be the distance covered, and one is just the distance that we've propagated, like upwards, just storing the amount of energy. So we're going to use the wavelength because we're looking at the distance traveled along, and the time that it takes for one wavelength to travel is called the period. So that's c equals lambda over t, and you could use this to work out the wave speed, but this isn't the formula that's given in the data sheet, and that's because there's another relationship between frequency and time period. So if we think about frequency, we're measuring 1 second worth of time, and we're trying to calculate how many waves have passed that point in 1 second. And we know that the amount of time that it takes for one wave to pass the point is called the time period. So if we have 1 second and we split that 1 second into these individual time periods, we can then calculate the total amount of waves that have passed this point. This is a relationship that you will find in your formula sheet. Okay, it doesn't just work for waves, you'll find it also is going to work for periodic motion. But what this means is that we can change this slightly, because this is the same as saying, I could just rewrite this a little bit as saying this is lambda times 1 over t. These two are identical, and 1 over t I know is f, so I could actually write the wave speed as c is equal to f times lambda, and this is on your formula sheet, okay, where the wave speed is in meters per second, frequency is in hertz, and the wavelength is in meters. And these are essentially the only things you'll be asked to calculate as such using these properties. We'll obviously go into more detail in more things that waves can do, but for now this is the extent that we can get to. Now let's look at how these things are all going to relate to looking at longitudinal waves. So longitudinal, second type of wave, we can also have all of these properties, but the difference is that longitudinal waves are when the oscillations are parallel to the direction of propagation. Okay, now it's very difficult for me to draw what a longitudinal wave looks like, so instead I've got a little bit of of a video that's hopefully going to show it in a little bit better detail than I could. So as you could probably see, this red line on the far left is pushing the particles along, and you can see these parts where we have a very high concentration, so where they're very dense together. These are what we call compressions. Okay, so compressions, I'll make a rough diagram of this afterwards, but compressions are where we have compressed all of them, and the gaps between them where there's a little bit less particles are called rarefactions. The key important thing with this is you can literally choose any particle in this short video that is on repeat, and if you watch it move, it will only ever move completely forwards and backwards. So each individual particle oscillates parallel to the direction that the wave is traveling in, even though the wave is propagating through the whole thing. So if you were to look at one compression and then watch how it moves, it looks like it's just a solid line moving along this. But if you look at the individual particles, they actually oscillate backwards and forwards. Okay, so my rough sketch of this, and I mean very rough, is this is a rarefaction, compression. This will be a rarefaction. This will be another compression. Then this will be a rarefaction, and this will be another compression. And now you probably got a better idea that this is going to propagate in this direction, and each individual particle is just going to move forwards and backwards. Okay. Now we can still apply the same properties to it. We can still have the distance between two compressions being the wavelength. So this is generally how we're going to do it. The difference between two compressions, because if we were to look at the difference between two rarefactions, they're much wider, and it's much harder to pinpoint the exact center, so you're going to get a much bigger uncertainty. And we're not a fan of uncertainty. We're trying to get as accurate a result as possible, so we're going to just make it the distance between two adjacent compressions. Okay, so just as a reminder, these are compressions, and these gaps here are called rarefactions. Now the wave speed of these things we can still calculate using this idea that c is equal to f lambda, and we still have the idea that the frequency is the reciprocal of the time period. These two things work for both longitudinal and transverse waves. The only difference with longitudinal really is what examples we have of them. So if we look at some examples, we'll do a list of some examples of transverse waves against a list of some longitudinal waves. So let me try that again. Longitudinal. There we go. Some examples of transverse waves that we should be familiar with. The biggest one is light. Because of that, we mostly work with transverse waves. Okay. There is another reason we mostly work with transverse waves. That's because they look like sine waves, and it makes it a lot easier to do mathy stuff with them. And we can also, I'll show you in a second, how we can turn something that's longitudinal into a diagram that looks like a transverse wave. So light is a good example of a transverse wave, and sound is a good example of a longitudinal wave. We can also have the example of things like seismic waves. So if the waves that travel through the earth when they're made up, when earthquakes happen, so when tectonic plates collide, split into two of these things. And so we have P waves and S waves. S waves are transverse, and P waves are longitudinal. Okay. If you haven't done anything on seismic waves, you won't really have to worry about that too much in A level. We don't really go over seismic waves, but they're just good as examples to know. So these are the main examples. I will say light is the thing we work with most, purely because it's easy to work with and it's the most interesting, to be fair. But let me show you now how we would turn a longitudinal diagram into a transverse diagram. So I'm going to leave these examples here, but I just need to make a little bit of space under here. So I can make a graph here that is essentially going to look and mirror each of these points. Wherever we have a compression, I'm going to have a high on this graph. Wherever I have a rarefaction, I'm going to have a low on this graph. So if I do it like this, you can find that it's going to keep oscillating between being high and low, and we get back to a transverse looking wave. So this is generally how we would analyze longitudinal waves. We'd first have to convert them into transverse waves and then be able to do all the sinusoidal maths. This is your introduction to waves and their properties. Thank you for watching.